Hey, so good afternoon, everyone. Today we are going to look at embeddings. So embeddings is the beginning of the story of RAG. RAG means retrieval augmented generation. Basically, it is a way of giving additional knowledge or information to LLMs without having to retrain them or fine-tune them, right? Because LLMs are trained on, of data, so they have knowledge, but they don't have all knowledge. Like they may not know, like let's say you have a document that you want an LLM to analyze, and there's some kind of additional information or context that you want to give to them. You could fine-tune and, fine-tune and train the LLM, with that additional information. But that is really for machine learning engineers. But for you as an AI engineer, you are not going to really, well, it's a good skill to learn. And there may be some situations where you would have to, where there will be a need for you to fine tune. Fine tuning an LLM basically means additional training on top of what it has already trained. And typically, the amount of information and data you need for fine tuning is much less, like 10 or 100 orders of magnitude. Uh, an order or two orders of magnitude, that's what I meant to say, lower. So, but in operational situation, you typically would say, okay, we cannot always do that. It doesn't make sense. We cannot always fine tune, right? In a dynamic, just in time, kind of situation, you want to still be able to give you that information. And that is where embeddings, RAGs come in. So today we are going to study embeddings and we'll understand what it means. And then we'll also talk about how we can use it to our advantage. So the objectives of this week, we will look at how embeddings work conceptually. We'll talk about what we call similarity and semantic similarity. Then we'll do a bit of visualization as well to, do visualization, just like we did visualization of prompt chaining, we'll do a bit of visualization of embedding so that we kind of get an intuitive feeling of how, that works. Then we'll look at vector databases, right? Um, databases are databases that allow us to manipulate embeddings in a more optimal, efficient manner, right? Because typically the regular databases that we are used to, that we use, the relational databases or even the document databases or even the um, um, all of these are not, they are designed to deal with data specifically. Um, data, when you talk about comparison or search, right? In fact, it's really in the area of comparison, not just the storage, right? Even though storage is a thing, right? Efficient storage, right? And retrieval, but search. So we'll talk about that shortly, right? So we have vector databases, and we have three of them we're going to look at. We have Pinecone, we have Chroma, we have Vice. Vice is Facebook AI. It's a library actually. So we'll look at that. Then we will continue to look at what we call RAG. Like I said, RAG is retrieval augmented generation. So it basically refers to augmenting the generation that GPTs do. Remember, GPT is a generative retrained transformer. So all the G's in that means generation of responses or text, right? So we will augment the generation of text that a GPT does by retrieving additional context. And that additional context is stored in the form of embeddings. So we'll retrieve that from a database and use it to augment so that the LLM will do a better job in generating the right answers that match the context that we're looking for. So we'll look at how we can do that with Python, and we'll look at how we can do that with JavaScript. Then the kind of project we'll look at is a simple Q&A API, right? Using the embeddings and using the RAG pattern. So what that means basically is I upload a document, right? And then based on that document, the AI is going to answer questions based on the document that I, uploaded. So we'll see how to do this using a local, because typically this actually makes more sense, right? When you are using your own LLM that you are running locally. Most of the hosted LLMs, right, or hosted AI already have these enhancements. So, it's not a big deal. They would do it, right? You upload documents to all of these, and they will be able to do stuff, right? So we'll look at some of those examples. Okay, so what are embeddings? An embedding is basically a numeric representation of the meaning of something, of the meaning of a concept, right? And typically, these concepts can be text, can be images, it can be audio, it can be sound, it can be anything, right? But what happens is that this information that comes in raw form, like text, image, sound, audio, it could even be any other format that you like, right? They would be converted into an array of floating point numbers, which we call a vector, right? Now, it's not just converted in any manner. It's not random conversion. So it's not like ASCII code or any other, or UTF-8 or Unicode. It's not just a mapping of characters to numbers. That's not what it is. Like it starts off by saying it's a representation of meaning. So it's actually mapping the meaning, not just the characters. And it is mapped in such a way that things that have similar meaning will have vectors that are close in distance. We are going to talk about distance, right? What we call the embedding distance, right? There is that concept. That embedding distance is actually a mathematical function. So I don't want to go into all the maths of it, right? But it's a mathematical function. So think about it like if we were using 3 numbers to represent, let's assume all the meaning in the world could be represented by 3 numbers, right? Those 3 numbers, there's what we can call, or let me use 2 numbers. I think it's easier. Let's use 2 numbers. So if for those who studied physics, if you have 2 numbers, you have magnitude and direction, or you have the x and y component of a vector. So it's still vector in that context, right? X and y component. So when you do that, you have what we call the resultant, right? The resultant is when you combine x and y. That resultant has a magnitude, it has a direction. And if it's even x, y, z, you have a resultant. That resultant is a combination of magnitude and direction, right? So there is this concept that vectors that are pointing in similar directions or in the same directions are similar in meaning. In fact, 2 vectors are the same if they point in exactly the same direction and they have the same magnitude, right? Even though the actual physical position, the spatial displacement may be different, right? But that also matters anyway. But same direction. So this is the same principle that is used when we want to calculate what we call similarity index between embeddings, because essentially an embedding is a multi-dimensional set of numbers. So it's an array of numbers. So it's multi-dimensional. It's not just two-dimensional, like we could say X and Y. So the position of a dot in X and Y. So X and Y will be a vector of two numbers, right? That tell us where a particular point is located on the graph. And then if you have another point that is located, it also has its own X and Y coordinates. And those X and Y coordinates, you can calculate how close they are together by using Pythagoras theorem, basically, right? Or how far apart. Okay, so now extend this idea to not just two numbers that represent the X and Y coordinates, but maybe 128 numbers that represent a multi-dimensional coordinate space, 128 dimensions, right? So to visualize that is impossible for a human being. And that's why we have methods in machine learning. We have methods that we use for visualizing these kinds of multidimensional spaces. We call them dimensionality reduction methods. And I'm going to show you how a few of them work. We have TSNE, we have PCF, principal component analysis, and a bunch of others, right? They basically reduce a large dimension like this 128 dimension vector that represents, the position of something in a 128 dimensional space, can reduce it to a three-dimensional space so that we can easily see what it looks like. We are going to do that when we get to visualization of embeddings. So that's what an embedding is. So when you calculate that similarity, you find that embeddings that have similar meanings will be the vectors that represent those will be close together. But different meanings, words or concepts or images that have different meanings, the vectors will be far apart and will point in different directions and so on. This is what embeddings are, and I'm kind of going to the mathematical basis of it just to make it more interesting, right? But at the end of the day, it's just a bunch of numbers. It's an uninteresting bunch of numbers. If you're just looking at the numbers, they don't make any meaning to you as a human being. You'll see 128 floating point numbers. You'll be wondering, what do these numbers mean? But these numbers actually mean something. Now, in the old days, right, embeddings were created by hand, by human beings, before neural networks became really powerful. People will have to try and look for a number that represents a man and a bunch of numbers that represent a man, another bunch of numbers that represent a woman and children and all of that. But it wasn't coherent because human beings were just using human knowledge. But with the advent of deep neural networks, it was possible for you to train neural networks on a lot of things. And one of the, you could now extract the neural network's own representation of its knowledge. You extract that representation of its knowledge, right? And when I say representation, it's actually going to be a neural net, a model, just like the model that you use to do the LLM, you call it and it gives you an answer. There are models that are trained to give you embeddings. So when you train models on a lot of information, it actually begins to crystallize its own understanding of these concepts based on all the knowledge you have given of trained it on. It begins to crystallize it, and you begin to see a lot of interesting stuff. Like if you train an LLM, then you pull out some intermediate layer in that network, and then you give it a word like man, and you take the embedding. You give another word like woman, and you take the embedding. Now, there are people who have done some interesting studies that the distance between man and woman is the same as the distance between boy and girl, right? And in fact, the direction, if you were to represent it with arrows, the direction that man faces, you'll find that the direction that the embedding, if you were to kind of use a vector arrow to represent it, the direction that man faces is different from the direction that a woman faces. That's the word man and the word woman. But if you now look at the boy and the girl, the boy faces a similar direction to the man, while woman faces a similar direction to girl, but they're in different points in the dimension space. So people have done a lot of studies on this embedding and come to realize that they actually they are better representation of entities than what a human being could come up with. So that is why we now have a situation where large language models or neural networks generally are used to generate embeddings. So you could even take a neural network that you trained on visual data, maybe a neural network that was trained to recognize handwriting. And you'll find that the embedding that comes from any image that looks like number 7 will have similar embedding. And any image that looks like number 5 will also have similar embedding, but that'll be totally different from embedding of number 7. So it is very interesting. So that's what an embedding is. So embeddings allow models to understand semantics. Now, the interesting thing is that when you generate embeddings, you can then use these embeddings to represent concepts. And then you can store embeddings rather than storing words or sentences or paragraphs. You can store these embeddings. Embeddings represent meaning, not the words. So you can also have the semantic similarity, which is the vector distance or the embedding distance or the similarity index between embeddings that mean things. And you find that things that have the same meaning, like I've said already before, the similarity index will be close. But things that have that their meanings are far apart, you see that the similarity indexes are also far. So where do we use embeddings? We use embeddings in search engines. In those days when Google started, before AI really took over, Google used to use a lot of really interesting techniques and heuristics and algorithms just to search for something. But if you search for something like white elephants, right? And elephants that are white, those would give you two different things, but they mean the same thing. So if you were to take embedding for white elephants and take embedding for elephants that are white, they will be the same. Now, so when you are searching for embeddings, you are now just searching for an embedding that is close to white elephant. It will bring you anything else that kind of sounds like that, right? So there were other ways we used to search for similarity. For example, searching if the letters, how many letters, there's this thing, I can't remember what it was called. How many letters do you have to change between two words for them to become the same word, right? There's a name for it, I've forgotten that. So there were so many different heuristics just to be able to calculate similarity between words. But now, with embeddings, we are not even just talking about similarity between words. We are talking about similarity between entire concepts, entire ideas, right? Because even searching similarity between words is not even enough. Because there's this thing we call an attention mechanism. A word can have two different meanings based on where it is in a sentence. You understand? So, for example, I'm going to look for really good examples of how attention can change meanings of words, right? So now I have a few examples here. So for example, so when you say something like, only she told him that she loved him, right? She only told him that she loved him. Or a word like something like the boy told the man that he had returned. The boy told the man that he had returned. Okay, that's a very good example of. Now let's look at the meaning of that word, he. The he in he had returned. Who is the he? Is it the boy or is it the man? So the meanings change. The lion killed the man killed the lion, right? So meaning now changes not just based on the words, but even the position of the words in a sentence. That one is called attention, attention mechanism, and all of that. But in human language, a human being is able to understand and grab these differences in meaning quickly without even thinking twice. But an AI would be really stumped. Of course, not AI of today. AI of today, all of that has been overcome. So embeddings help to represent such differences, right? Not just differences in meaning or similarity in meaning of different words, but differences in meaning of similar words or differences in meaning of the same word because it is in a different place in the sentence. So embeddings are very good for search engines because then when you convert the search string into an embedding, it is now easy for you to find everything else that matches that embedding or that is close to that embedding. Semantic similarity detection, right? Then recommendation systems. Recommendation systems are like one of the best in using embeddings. Because what happens in recommendation system is that your preferences are converted into embeddings. Embeddings can actually represent your preferences. So for example, you watch movies on Netflix. All of the movies you have ever watched, it can be plugged into an LLM or not necessarily an LLM, but some kind of neural network that will generate an embedding that represents your preferences. And then that embedding that represents your preferences will be compared with other people's embeddings of their preferences. And we'll find that people whose embeddings are closer means they have similar preferences. And that's how they'll come and tell you, okay, that this other guy also watched this kind of. Do you think that they were going to search all the movies that the person watches on Netflix? Or if you go to any what do you call it? Um, e-commerce sites, this book, people that bought this book also bought this other kind of book. What's going on there is that there is actually embeddings going on. Well, there are some websites that don't have AI. They basically have, well, it's still AI, AI is artificial intelligence. So if you were to write some hard-coded set of rules that does, like, still AI, that's what it is, rule-based, right? It's not machine learning or something, but it's rule-based. So that's what recommendation systems are. Clustering. Clustering is where you want to group things that are similar together into groups, and things that are different will be in different groups, right? That's clustering. And clustering also uses embedding, because you can use embedding to represent the similarity, the things that make people similar, and the things that make people different. Then we have RAG, which is like retrieval or augmented generation. So we have GPTs that will generate a response, but you inject an embedding into that, and the LLM can do a better job of fine-tuning its response to match you. Then classification. So we have this chart here, kind of shows you how embeddings work, right? You will see that words that are similar are close, while words that are different are far apart. Words that are synonyms are close. Words that are antonyms, that is opposites, will be on opposite sides. So you see decision, loss, recall. This is in the context of machine learning anyway. So you see this is embedding. There's this interesting thing. I'm going to share this link, which I would like us to look at. It's called the embedding projector. This was actually a tool built by Google TensorFlow. It allows you to upload words, or you can even just check. There's this thing called Word2Vec. Word2Vec is a tool, a library. In those days, when I was talking about had humans kind of coming up with some heuristic to generate embeddings, Word2Vec actually generates embeddings. Even though these days Word2Vec still does a really good job of generating embeddings, right? You give it words and it's going to give you corresponding embedding, which is basically a vector. That's why it's called Word2Vec. The vec there means vector. So it's going to give you a vector, which is a vector is essentially an array of numbers, of decimal or floating point numbers, right? So Word2Vec will generate embeddings for you, and embeddings are typically similar. We're going to try a bit of Word2Vec examples here, just for you to see what it means. But before then, we need to be able to measure the similarity, right? You should be able to measure the similarity of embeddings so that you know whether they're actually similar or not. So let's try something. Okay, so here we have different ways of generating the, again, so there's something I want to mention here. Remember, embeddings are multidimensional. Some embeddings can be up to 128 numbers. Some could be maybe 112, 100, 80. Some could be even more. You cannot visualize that. You cannot plot a point that has 128 coordinates. The highest we can plot is a point that has 3 coordinates. That's X, Y, and Z, right? So we use what we call dimensionality reduction algorithms to reduce the dimension. So like this one, the dimension is 200, right? Basically a vector of 200 numbers that represent the 200 points, or its coordinates in the 200 axis coordinate system, right? But we need to reduce it to just 3. And when we reduce it to 3, we can now visualize it. That's what PCA does. That PCA is a principal component analysis. It's just a tool that we use for dimensional field reduction. When you do that, it actually gives you an idea of which ones. You take the top 3, and those top 3, you plot it on a 3-dimensional, you can drag and drop this thing around, right? And so you have words like this. Now, there are too many words in here, so we're not really seeing anything useful here. So what I want to do is, you can actually upload a file that contains words, right? I can, load a file that contains words. The words has to be what we call a TSV. TSV is tab separated values, right? Tab separated values are like comma separated values, except that you're using tabs to separate the numbers. An easy way for you to create tab separated values is just to create a Google Sheet, right? So I'm just going to create a new Google Sheet, and then I'll type in some words here. So what you typically will do is you can just type any words. You can have one row, and then you can have columns. But let me just do one single column of words, right? Something like maybe let's see, because I do not have a lot of time. I'm going to ask AI to generate words for me, right? And I will just log it in. So we can go to any of this. Let me do this on screen so we can see, just to make it more interesting. So I'm going to let me ask Node to just generate for me a list of words. I need a list of 20 words to use for embedding um, examples. So we'll just do 20 simple words. All right. So I take these 20 words, I'm going to copy them, and I'm going to put them in here, right? Then I'm going to save them download it as tab separated values. So you see it here, tab separated values. So I'm going to do that. Download file, download, right? Choose tab separated values. So it has downloaded it somewhere on title spreadsheet in here. So I'll take note of the location. Then I'll go back to this embedding projector. So I named that file words for embedding. So it's easy for me to identify. Right, so I will choose a file that is not vectors. I'm going to just load words, right? So I'll click on this and I'll go to my downloads, words for words. Yeah, so I'll do that. So it already computes the PCA. So I've uploaded that. I think there was a problem. Let me see. I need to choose. Okay. Number of it's okay. So word to vec needs to have 10,000. I don't want word to vec. So iris is going to be I want custom. Okay, well, so I was kind of just trying to show how words, just representing it in this space so that it gives us an idea. So iris is a database that contains it's a database that contains classification of flowers, right? So based on classification of flowers, so you see this, you can see it's moving around a bit. So you see the embeddings depending on basically a 3D representation of this. So this is just a way of visualizing that. I found that I cannot upload my own customized data. I thought I could. If I load my own data, it has to match the number of there has to be 150 of them here. I could do that. Let me see if I could do that. So let me ask for 150 words. At this point, it becomes more difficult. Okay, so 150 words. I'm going to copy all 150 words and put them in my spreadsheet. And I'm going to double check that they're still 150. I take out this. Okay, so we have 150. Then I am going to download it. First of all, I'm going to call this words for embedding. So words for embedding. Okay, then I will download as TSV. Okay, then I'm going to re-upload that here, and hopefully it matches. Okay, so it matches. So we kind of have, we now have my own words in here rather than the, so you can see you have embeddings, boy and man, broke friend, speedy. So, well, again, it depends on how the network was trained, right? It should be able to, things that are close together should have, like these two up here are close together, right? But this is not really trained on those words. It's trained on iris. So this is really just using level. But this was me just trying to show you how embeddings look like. Okay, so to continue, how do embeddings work, right? It is a three-step process, right? The first step is the text is broken into what we call tokens. Tokenization. So a token is kind of smallest representation of meaning, which typically should be a word, right? I don't know if there are tokens that are less than a word, right? But you could have situations where a word can be split into two, but most times a token kind of matches a word or two words or a phrase. So this is a good example. Artificial intelligence is amazing. It gets split into 4 tokens, which correspond to the 4 words. Then you now have those 4 words will be sent to a pre-trained neural network, pre-trained model, basically, that will take those tokens and convert them into a numeric vector. And this vector does not necessarily amount to, finding the embedding of each of these words and putting them. No, it goes beyond that. Even though the first step will be take each of these words, find the embedding of each word. But then there's also, like I said, the attention mechanism that is used to further adjust, right? This, even though initially, well, you get an embedding where each of these numbers represent what the neural network thinks or sees, or its internal representation of the meaning of these words. So you would now see that these are numbers, like I said, floating point numbers, basically numbers with decimal points. And these numbers can be anything, right? So in this case, artificial is mapped to this number 0.021, intelligence minus 0.33 is 1.24, and so on, right? And it's a high dimensional thing, right? So you can see typically up to 384 dimensions or to 1,536 dimensions. So these vectors will capture everything. They'll capture the context, they'll capture the meaning, and they'll also capture the relationship between the concepts. So now how you make some sense out of it is you now calculate what we call similarity, or the vector distance, which is the distance between the embeddings. So if you have what we call cosine similarity, this is one of the methods of calculating, and that's the most common method, right? So in cosine similarity, if you have one means that they are very similar. 0 means that they are unrelated at all. They are not, there's no real correlation or relationship between those two words. While -1 means that they are related, but they are opposite, in opposite directions. So for example, if you were to calculate cosine similarity between man and woman, you get -1. But if you were to calculate cosine similarity between man and boy, you get 1. And if you were to calculate cosine similarity between man and flower, you get a 0, right? So that's one way. Then the second is Euclidean distance. That's what I was trying to remember. This is the terminology. So Euclidean distance is basically the number of times you have to transform one word or one vector for it to become the other one, right? That's Euclidean distance. Then, sorry, that's not the Euclidean distance. Euclidean distance is a mathematical function that you calculate. You take those two numbers and you do a mathematical calculation between them. Then dot product. Dot product is just a matrix product between those two vectors, right? A matrix dot product or inner product. Okay, so those are 3 key elements of embedding, right? You first of all tokenize your words, then you get an embedding for those tokens, and then you can now calculate the vector distance. Okay. So now we want to talk about, so we are now going to do a bit of hands-on on how you can create embeddings. And like I said, embeddings, you have models that will create embeddings for you. So you just send them whatever you want to send them, and they'll return embeddings for you. You can send them entire sentences. You can even send it in batches. You can send a bunch of words in batches. These days, LLMs are so good that they'll give you embeddings for entire things. So it gives you a whole lot of context and meaning, right? So yeah, let's get to it. Are there any questions at this point?
Yeah, I wanted to ask.
Go ahead, go ahead.
Oh yeah, sorry. I wanted to ask, when we are talking about the tokens, is it one token for every word in a word in a sentence being tokenized?
It's not always necessarily a word to a token, but in most cases, a token will actually correspond to a word. But there are times when you see a token that has 2 words in it or 3. I've never really seen a token that had half a word, because that wouldn't really make sense, right? So, but that is even in the context of LLMs. There are other kinds of tokenization, speech, that is sound, right? Comes in. You could also tokenize it. So how do you tokenize sound? The sound waves are coming and so on. So, but there are tools, there are libraries that allow you to do all of this. Okay. Yeah, so the word I was trying to remember is the Hamming distance. Hamming distance or Levenstein distance, right? Is basically how many substitutions or transformations you do to one word before it becomes another word. That's what people used to use before, but it's not a very useful method these days with embeddings. So let's try a bunch of, just let's see how we can get some embeddings, and then see. Yeah, let's see. So the first thing is to use OpenAI. Well, OpenAI, I don't really have, like I said, I can't access OpenAI at this point. They don't give you a free API. But if you did want to access OpenAI, this is how you would do it, right? You would just the same way we have been doing it, except that we're going to use client.embeddings.create. Okay, we're asking that it creates an embedding. So you specify the model. The model has to be a model that has been trained for embeddings, not a model that has been trained for generation, not a generative model, but an embedding model. So this is the main thing that you need to pay attention to. you are going to use basically the same API call, but look for an embedding model, not a generative model. And then we can then look at how this look like. So that is with OpenAI. Hugging Face, on the other hand, is quite accessible. So I am going to make a code block, and this is Hugging Face. Now let me add the .m file with the necessary API keys. So I'm going to create a new file, .env. So anyhow you want to be able to access your API keys, you can do that. And then let me bring in 1 minute. Let me go look for my secrets. Okay, so I have my secrets now. So the Hugging Face secret is HF API key. I'm going to put that in here, and going to import .env load. So I'm just going to ensure that I load .env. Okay, so let me run this. So we'll get the Hugging Face sentence transformer, right? The sentence transformer wasn't saved. Okay, so there was a bit of a delay, but everything is fine now. So you can check this out. So you see that they have a sentence transformer. The sentence transformer allows, and this is the name of the model. So essentially, a sentence transformer is a class that, or a kind of model that generates embeddings. So when you do that, you just run model.encode, and it's going to give you a vector. And this vector is going to give you embeddings for it. Okay, so it still allowed me to access, even though it seems it did not read my token, HF token. Okay, it should be HF token. So let me go back and change this to HF token. Okay. All right. So if I run this, hopefully I should not get that. Shouldn't get that error anymore. So it generates, yes. So you can see this, right? I didn't get a good answer before, but you can see the length of the embedding vector is 384. So there are 384 numbers. That's the dimension. So, and this is the first 10, because this vector 10. So this is the first 10 numbers in that embedding, right? So like I said, at the end of the day, this embedding are just a bunch of numbers. Nothing really interesting about it. You look at it, it doesn't really mean anything, right? But it does. There is knowledge embedded in this embedding. And that pun was deliberate. So there is knowledge in the embeddings. So you can do a whole bunch of stuff with this, right? So we can we can, the other thing you could do is you can give, okay, I'm going to come back to the other embeddings like Gemini has as well. So remember, we're able to access uh, embeddings on Gemini. So let's see how we can do that. So let me just get some, we can use a Gemini, the Gen AI. So we already have a Gen AI. I think we did a bit of that already. So last week we did that. So let's see. So you import Gen AI, you get the client, then you put the API key. So here I'm going to just load the API key, os.get, and so Gemini API key. I'm going to, of course, do all of this here. Then I'm going to add the Gemini API key here, the .m file. So let me go find my API key. Okay, the Gemini API key. Okay, so I have that here now. Okay, takes a bit of time. Maybe I should just manually save it. Right, so I can run this. Okay, I think it ran before it. So when you look at this Gen I client API key is this models embed content. So this should be contents. They have changed their interface. Okay. Okay, let's just print the response and see what it looks like. Okay, so you have embeddings, content embedding value. So you get this, right? Um, so it should be response embeddings. So it should actually be response embeddings. Okay, so this is how you extract it. I think there's a slight change to the API. So first of all, you pass in all the contents. So this allows you to pass in multiple texts, right? So I could pass in any number of what we call batch. You call it in batch. Well, okay, it's nice. Then, so for each of these, you can access it by embeddings X, Y, or Z. So you can actually have embeddings, uh, we could have all three. So we could just, let me see how this looks like now. Or I could even put in a data frame, like, so it's easier to see and compare. Yeah, let's do this. So I have a response of embeddings. So I will now put all of these embeddings in a pandas data frame so that we can look at how embeddings look like. Yeah. So this is very simple. So we'll start again, we'll run the Google. It gives us embeddings. We put the embeddings in a data frame, and it makes it easy for you to view and to see how it looks like. Right. So these are the actual values of the embeddings. So you see that embeddings are basically just numbers. And since I requested for three different sentences, right? So it's giving back three answers as well. And each of them is an entire list of numbers. We can check the first one, for example, embeddings 0, which is the first one, dot values, right? That would be the first set of numbers. We can do statistics on it. So I could actually just put it in a data frame as well. And then let's see what it looks like. So the most interesting thing here you see is that there are 768 numbers in this embedding. So Gemini is giving us embedding of 768 characters, or sorry, 768 numbers. So the question you will ask yourself is, wait, the sentence I passed in here, machine learning helps computers learn from data, was just 7 sentences. So why am I getting an embedding like 700 something, right? Again, that's because the embedding is for the entire sentence, and each sentence has its own meaning. It has meaning, it has context, it has nuance, it has all kinds of things. So these 767 numbers are a way of representing all of those contexts and nuances and everything, right? Inside the that sentence. Then you can use that for analysis. So speaking of analysis now, an interesting thing you do after you have done the embedding, you've gotten the embedding, right? Which is basically a list of numbers that can be very long. So this is 768 for the Google. For sentence transformer from Hugging Face, it was 384 numbers, right? That's the length of the embedding. Then what you can now do is, what do we use these embeddings to do, right? How do we store them? How do we manipulate them? How do we even make sense of them? So the first thing is, let's check out the similarity, right? So let's see how we can do that. So cosine similarity is actually a very, very simple, you know, you use, it's a simple mathematical equation, right, that is based on linear algebra, right? You even see it uses NumPy. So let's do this. Let me just add a description here. So this is cosine similarity. So there's a function here to do this, right? We use NumPy, so we'll get NumPy. So NumPy has a sub, no, a sub module called linear algebra. So you are doing a norm. A norm is basically, there are three types of norms, right? There's norm one, norm two, norm three. I won't go into all the different details of it, but a norm is just a way of calculating the distance between 2 points in any space, in any n-dimensional space, right? So in a two-dimensional space, right, the equation of the norm actually reduces to a Pythagoras equation that we know of, right? The norm between 2 points is you either take square root of x0 minus x1 um, squared minus yeah, well, it's Pythagoras is the square root of the difference between the 2 points. So x0 minus x1 squared plus y0 minus y1 squared. You take the square root of that. Plus rather, not minus. So you take the square root of that. So that gives you, that's the distance between those 2 points. That's really what the norm, that's the second norm. The first norm is just x1 minus x2, x1 minus x2 plus x1, x0 minus x1, then y0 minus y1, so the distance between the two. So yeah, but norm is basically just a way of calculating the distance between two points in space. So in a multi-dimensional space, the general equation is there. In this case, you just use this function, right? And you calculate the norm. I'll still go into details on this maybe in the next class. So if you have two vectors A and B, right, you can pass them into this function and it will then calculate the cosine similarity using this function, right? So that's how this is done. So to now do what we have, you can then do embedding and then calculate the difference between the two embeddings. So you can actually send two words like we did here before. So you can see we already have the embedding 0 and the embedding 1 that Google gave to us. So you can now calculate the cosine similarity. Of embedding 0. Is it embedding 0 dot value and embeddings 1 dot value. Okay. So values should be values because values. So that was a typo. Should be dot values. Since it is okay. Yeah, I need to import NumPy. So you get this as a cosine similarity. So now let's pull everything together, right? And do an interesting function. So we'll now say, okay, similarity. You can just define a function called similarity. And you can pass in two words, right? String one, or yeah, text one and text two. So of course, the first thing you would do is to run the two of them. Let's assume you're using Gemini. So we'll just do this. We already have the client, so I'm not going to redeclare the client. But let's assume we had the client already. So we have the client and right. So the contents will pass in are the two texts that we want to calculate the similarity. So we have text one and text two. Okay, and we have already chosen this model. So there are a lot of models for text embedding, by the way. So it's something to go check out. I think we can go look at both Gemini and Hugging Face, right? You see a lot of different models you can use for embeddings. Even on Open Router, you see a lot of models you can use for embeddings. So I pass contents as the two texts. So the response is going to give me embeddings for those two texts. Then I now do the cosine similarity of the two responses. So response embedding 0, the value is response, right? So with this, we now have a function. So now that we've written this function, we're going to do a bunch of interesting stuff. Remember, I had a list of words, which in a tab separated list. In fact, I'm going to ask Claude to generate for me a list of words that are similar and dissimilar. And then we'll run cosine embedding for them. So I need a list of words that are a list of word pairs of comma, we can say comma separated word pairs that are both similar, and also not similar for testing my similarity code up to 30 words, 30 word pairs. Okay. My prompt wasn't a very nice prompt. Okay, so here are 30 word pairs. Oh man. I don't know how I did this, but so my prompt was terrible, obviously. So let's improve the prompt. I need a list of, okay, so I am running tests on my code, on my word similarity code. I need a list of words in pairs that may be similar or not. I need a list of, let's say, 50 words arranged in pairs in comma separated pairs that may be similar or not similar to carry out this test. Do I get a better response? Right. This was a better prompt. So this is a very good example of writing terrible prompts and expecting magic. Okay. So I'm going to take this and then I will put this in uh, my sheet. Oh, this is not working. Okay, so I'll do it differently then. Just going to paste them here. Process the words. Okay, so I have this, it's not looking very nice, but I will process it from here. So words equals word pairs, but split with and then that's going to give me a bunch of stuff. So yeah, okay, let's just go ahead with this. So for split and I think I need to do a replace. I need to replace the commas. This is data cleaning, by the way. So I'm going to replace the extra space after commas with just that. And expected to got one, right? So there happened to be an empty line at the beginning. So let me take this. Okay, it will still work. Let's keep the empty lines. Oh, before not, not. And I thought I was doing JavaScript. Okay, so yeah, I would like to put this in a data frame and so that it's easy for us to see how it looks like, right? So I will can always have a similarity. Word and similarity, append a list, right? Then we do a new data frame. And then we print data frame. Okay. PD.data frame. So this is taking a bit of time. I don't know why. Right. So we now have this data frame. So you can see the cat and dog similarity index is high, 0.6, happy and sad, run and walk, 0.54, bright and dark, 0.64, large and small. Things that are not similar will always have these large numbers. Opposite will get close to, opposite should actually be -1 if we were doing this right. So I'm surprised that we are getting like fast and slow, hot and cold. Similar words should have lower values. This doesn't seem to be calculating what I wanted to calculate, because they all seem to look like they basically have the same values. So okay, so there's another way we can calculate cosine similarity, which I want to try using Hugging Face. So Hugging Face has its own similarity calculation function, right? So we would try that rather than using this linear algebra method, which seems to not be giving me what I want. It's essentially giving me it's almost the same value for everything, right? So let's adjust this a little bit. Let's adjust similarity again by using not the cosine similarity, but using a Hugging Face's approach. So with Hugging Face, you have the util function or the util module. The util module in sentence transformers has the cosine similarity. So let's see how that works first. You basically will give it the same two embeddings and it will calculate. So let's try this. Til dot cosine similarity. So most of these libraries have one function or the other that does cosine similarity. So I'm going to rerun this using the new version. And we'll see what we get for cosine similarity. So this is cosine similarity. We are still using Gemini, by the way, to actually get, we're not using a sentence transformer. I will come back to that. We are still using Gemini. Well, the other thing is I really didn't need to rerun the embedding part, because the embeddings, the same words, the embeddings are the same, unless I want to use a different thing to generate it. So here, of course, it's giving me tensors as the response, but you see the values inside the tensors. It still looks like it's the same kind of thing, right? The numbers, it's still similar numbers what I had before anyway. So typically when you are doing this, you have to decide, okay, what is the threshold, right? When you are dealing with embeddings and similarity and cosine similarity, it's always a good idea to like ask yourself what number makes sense in terms of, okay, these words are similar, these words are not similar. Yes, go ahead, Kinika.
Okay, sir. I wanted us to see, I believe we can change the words. What if we like edit the words ourselves and just like change the maybe girl, if there is boy, change the girl to man. Let's see how close that will be. Because this one is seeming like words are opposite, but as if they are still close. So let's like this man and woman, let's change to man and boy. Let's see how close they will be. Like where you did where the main text was.
Okay, let's try. Yeah, let's try similarity of words that are similar. Okay, I think we can do that. So let's try similarity of words that are similar. First, man and boy. Then I'll let this one run. So while it's running, it's 0.55152. Now let's look at the similarity of woman, man and woman. So you see, well, man and woman is higher, of course. Man and boy is closer, but I was expecting it to be really close, but it cannot really be that close because even though man and boy are similar, but there are also differences, so this number still accounts for the differences. Now let's try using embeddings from Hugging Face, right? Instead of using embeddings from Gemini. So I'm going to use sentence transformer approach so that I can get embeddings from Hugging Face. So let's put this. So instead of response, the client is the Gemini client. But let's go back and check what we had from Hugging Face. So we just did sentence transformer. We create a sentence transformer model, and then we can encode any word. We can also encode. Let me see if we can encode multiple. I think there is a way you can encode multiple. Yeah, I'll show you that shortly. So, so we start with a model. So we're not going to encode the vector here. Rather, when we want to do the similarity, we will now encode. So you could say vector 1. You encode text 1, vector 2, you encode text 2. Then you just calculate they are using their own similarity function. Okay. So let's call this Hugging Face similarity. Now let's do Hugging Face similarity from so HF similarity between man and boy. Then HF similarity between man and woman. That's interesting.
Oh, sir, sorry, sir, to cut you in. Does that mean that even this embedding has a lot, like it's
Yes,
affected by LLMs also, type of LLM?
yes, the embedding values depend on which embedding model you use now. That's why it's very important when you are doing, you need to be sure of the embedding model you are using. If you have a really good model, then you get good embeddings. But
So, sir,
if you
which
don't
one
have
would
a
you
very good
recommend?
model, Gemini, Gemini. Hugging Face you can use as well, but when it comes to language, Google is like, I would still say Google. If you have access to OpenAI, you can also try, right? So now the next thing I would like us to do. So remember when we were trying to use that, uh, um, graphical embedding projector to see how we can do this, right? You can also write your own code for it. So, before that, let's look at, okay, we'll come to that. maybe we'll talk about vector databases in the next class. But let's say I want to, I can still do, let's do an example. Again, this is another example that we can do with embedding distances, right? So the first thing is that I want to see if we can use the dimensionality reduction to reduce the dimensions of the embeddings and then plot it graphically so that we can visualize it. So this, but first let's do this, right? What this is doing now is you have sentences. So you have 1, 2, 3, 4, 5, 6, 7 sentences here, right? Then we are going to now encode these sentences, still using Hugging Face sentence transformer, right? Then we will encode it to get the embeddings. Then we are going to calculate the cosine similarity between each of them. And then we'll display it. So let's run this one. So again, you have 1, 2, 3, 4, 5, 6, 7 sentences. So it's actually giving you a matrix. This matrix is similarity between one sentence and the next. So for example, this one that is 1.0, that is the similarity between a sentence and itself. I bought a new car, right? The vehicle was parked outside. This is now similarity or cosine distance, right? Between I bought a new car and the vehicle was parked outside. You see it's higher. Similarity with I am cooking rice is lower. Similarity with artificial intelligence is transforming industry is lower. Similarity with deep learning models using neural networks is lower. Similarity with the food tastes delicious is lower. But this last one is he drove his automobile to work. That's the similarity between I bought a new car and he drove his automobile to work. You can see it's higher. And the reason is that the subject matter, this one is talking about, cars, right? So everything that is talking about cars, you see they have higher similarity. These first two, excuse me. I bought a new car is talking about cars. The vehicle was parked outside is talking about cars. So that's why these first two have the high similarity. The last one is also talking about cars, right? I don't know if I can. The last one is also talking about cars. That's why its similarity is also high, right? But these three in between is talking about food. In fact, talking about things that don't relate to cars, these three. So that's why you see their similarities. So kind of, you need to have an understanding of it. Now, but what you see there is that anything that has to do with cars will have high similarity, and anything that has to do with that doesn't have to do with cars. But on this second line, right? Remember the thing that has one. The second line, the entry in the second line is the vehicle was parked outside. So again, anything that has to do with cars will also have high similarity, like this one and this one. But these other three don't have anything to do with cars, so they're basically very low. Now, but the third one, it says, I am cooking rice. So that's the one that is one. Anything that has to do with food, well, there's nothing else that has to do with food. The fourth one has to do with deep learning. So you see that it will have a similarity with this one. Okay, these two have a high similarity, 0.3, because this is talking about AI as well and deep learning. This third line had to do with food. That is, I am cooking food, as you can see. So this other one that has to do with food, the second to the last, will also have a high similarity to the food stuff. I don't know if this graph, the way this array is listed out, is easy to understand, but it's like saying this first line and how the similarity against all of this. I wish I could plot it in the matrix so that it would be easier to see. But you can do what we call dimensionality reduction, and then you can plot it. So there is sklearn has a function called tsne, T-SNE is one of the methods of dimensionality reduction. So with this, we can take the a high dimensional value vector like the 700 and something that we have here and reduce it to just 2 dimensions, and then we can use it to plot. So sklearn uses this T-SNE, then it has what we call fit transform. The fit transform is going to do a dimensionality reduction operation. If you want to know how that works, we are going to actually do that next week in the machine learning class. So you're going to get points, and then you now plot those points against each other, and then you can then annotate. Each of these points represents a word, right, in the embedding. Represents a word in the embedding. So we already had embeddings here, right? So we can now plot this, right? So you will see perplexity must be less than n samples. Let's see what we have for embeddings first. I think I missed something. Oh, there are a lot of embeddings. Okay, so I think the issue is the dimensionality reduction. The number of samples I have is small, while the dimensionality is very large. So it's I need to figure out how we can minimize that if we're using, yeah, but this is 368. Let me run it again. I think the number of words are too few. That I think is the issue. Okay. So let me use these similarities then. So things, which will give me complexity must be less than number of samples. Let's see, shape, what's the shape of We transpose it. Let's see if that works. Okay. So I think I should have transposed it. Okay, so this might not be a very good representation, but yeah, this is just like giving you an idea of position of. But this is a lot more than it should be. This is plotting each of the rather than each of the words. Anyway, so we'll look at this dimensionality reduction. But what I just want to show us here is that you can use cosine similarity basically to calculate the kind of the similarity, the difference between embeddings. That's a very, very important operation that we need to do. So I'll just round up with the second part of this before we go into next week. Well, sorry, next class we'll look at how to put all of this, all what I have kind of introduced. I want to introduce everything today, then we'll pull everything together. So after you have gotten your embeddings, the question you'll be asking yourself is, where will I store these embeddings, right? Embeddings are stored in vector databases. So a vector database is a special database that has been optimized specially for storing embeddings, right? And remember, these embeddings are vectors that have a whole lot of numbers in them, right? As you can see, between 300 to 700, sometimes up to 1,500 for each word or for each concept, right? So what you now do is, for these embeddings to become very useful, you have to be able to store them fast. You have to be able to retrieve them very fast, right? But more importantly, you have to search fast through the whole essence of database is being able to search, querying and searching very quickly. And not just searching, but similarity search, because for vector databases, the most important thing is similarity search. You want to be able to search between embeddings that are similar, that have, based on the embedding value, whether you're using a cosine similarity or dot product similarity, right? To search that they are similar, and then pull out all of the entries in the database that are similar to the embedding that you supply as a query string, right? So while the traditional SQL and NoSQL databases they are made for database searching on normal data, but they're not optimized for high dimensional vector operations. They're not optimized for similarity search. That's why if you try, in fact, in some of these databases like SQL, MySQL, PostgreSQL, and so on, you'll be hearing of things like context search or text context search. That's the closest that they come, right? But they're not optimized for this fast similarity search, and they're not optimized for millions, billions of vectors, which is what you would store. So with vector databases, that solves this problem, right? So some of the core features of vector databases, you have indexing for similarity search. This matters because when you can index for similarity search, you can get 100 to 1,000 times faster queries to run, right? Secondly, it's optimized for high dimensional vector support, like we've said. So you can store vectors of up to 384 to 4,096 dimensions, which a lot of LLMs and embedding, models would generate those kind of large vectors for you. Then you also have what we call metadata filters, right? Which allows you to filter, additional information that are not necessarily in that embedding format, maybe just normal clear text like you're seeing. Then you can also have hybrid search. So you can search both keywords and vector. So remember, a vector database allows you to store vectors and then as indexes or as keys. And then in the same row as a vector, you can store additional information. That's really how it works, right? You store a vector, that vector is used as an embedding, right? And then you store the actual plain text data that vector, embedding vector represents. So it allows you to search for both keywords, right? And also to search for embeddings. It's scalable, and like I say, you can have millions, billions of vectors stored there. Of course, persistence, so vectors are stored safely. You can have versioning, and then you have RAG integration, which we'll talk about later on. So we have a bunch of popular, vector databases that we can use. So we have Pinecone. Pinecone is fully managed, it's cloud-based vector database, very fast. It scales automatically. It can filter metadata, so you can use metadata to filter its, what goes into it and what comes out. It's designed for production RAG, basically, for production retrieval augmented generation. Yeah, so when we come back, we're going to look at Pinecone, creating an account on Pinecone. It's a cloud solution. It has an SDK which you can easily use. You import Pinecone, then you create an instance Pinecone client, right, with PI key, and then you can do stuff with that. Index, you create an index, and then based on that index, you can offset, you can insert, you can create, and so on, right? So you can put text along with vectors. So that's the most interesting thing. You put normal text, which you can put as JSON strings, as you can see, or JSON payload, and then you can put the vector along with it, right? So the vector becomes an index, or yeah, basically a vector becomes an index, and that's really what a vector database is, right? The vector is an index that you can use to find things. So that's Pinecone. Then you have ChromaDB. ChromaDB is open source, so we'll use that a lot. You can have your own, you can have it locally on your own computer, right? So you can run an instance locally, or you can host it on your own VPS or hosting, server. Or I think you can also use their cloud version. So you have local or hosted. And it's easy for you to embed inside an app. So it's good for prototyping, and it works very well with LangChain and Llama Index. So you can also see a sample of the code, how you can access it and use it. So you see here, it has a client. You import ChromaDB. You create an instance of the client, and then you create a collection. Then from that collection, you can add stuff with IDs, you pass in embeddings, you pass in documents, right? So that's how you use Chroma. We'll look at it in detail again when we come in. Then we have FISE. FISE is Facebook AI Similarity Search. So it's not really a database per se, but it's a library which you can use. But you have to configure it, and you have to build your own database around it. It's mostly just for similarity search, and it's very fast, right? It uses what we call SIMD, which is single instruction multiple data. So it can run very fast on GPUs. So if you have GPUs, you can set that up, right? And you will build your own database around it. But it's commonly used for research and for custom systems. So you can also see how you use it. You import, you can do index, you create an index, and then you can add vectors to the index. So we are going to look at how to use all of this very shortly. So I think that's more or less the that's how you use, that's vector databases. So now, to combine all of this, right? You combine all of this together, and that's where the real thing is. How do we pull all of these things together? Embeddings, vector database, and then you create what we call a RAG. So this is really the 6 steps to it. First of all, you take data, you split it into sections or chunks that are made up of maybe 200 to 500 tokens. So for example, if you want to create a vector database of, let's say in your office, you have a database of staff information. Now, of course, your LLM, the LLM you want to use does not know anything about your staff information or anything like that. But you want to be able to use LLM to do, natural language search through maybe HR information to know, okay, it is this person's birthday, or even maybe a company that has procedures, and you want to be able to search through those procedures. And maybe you want to write an AI tool that will help to that people can easily access and search and have access to those procedures. So the corpus of data that you have, that is the procedures or whatever, that is what you want to make available to the LLM so that it can easily search. So what you will do is you first of all take that corpus of data and break it down into smaller chunks or into sections. That's the first step. Break it down into smaller chunks. Each of those chunks will be maybe 200, 500 tokens. So if we go by a simple guideline that a token is plus or minus a word, so you can say, okay, break it down into paragraphs of 200 words, 200, 300 words each, or 400 words each, right? Then for each of those chunks, right, you run through an embedding LLM, like we just did, and you get embeddings for each of those chunks. Now, these embeddings could be of 300 to 700 or more in length. So you are going to get a vector of that length, right? Then you store the vector in a vector database. But remember, the vector is just an index. That's what you use to search, right? So you store the chunk in the same row as the vector and additional metadata, right? You store it in the database. Then when the user now asks a question to say, okay, can you explain to me the procedure for calling a cab, based on our company's guideline? What you now do is you take that question that the user has asked and you convert it into an embedding, right? Again, you just call the AI endpoint or model that you have, Gemini, whatever, pass that question in, it comes back with an embedding. That embedding, you now use it and say, you pass that into the vector database, and the vector database will search for closest matches to that vector, that embedding that came from the user's query. The vector database will search, then it will retrieve the top matching results from the vector database that matches the embedding that you passed in. You now take that context, right? You now pass it to the LLM. You pass those documents to the LLM as context, in addition to the original query that the user had asked. The LLM will now use that additional context that you have provided to it, and it will be able to go through it and answer the question, right? This is, when you hear RAG, this is basically what RAG is: retrieval augmented generation. So why does this matter? Because the LLMs do not have those additional knowledge or information. The LLM is trained on information, data, corpus of data from the internet, right? So that's all good, but it's not trained on everything. Specifically, it's not trained on that specific area that you want it to answer questions on. So because it's not trained on that, if you don't boost or augment, that's where the word augment comes from. You are essentially boosting the LLM's knowledge or source of data, right? By pulling that information from your vector database. That's why it's called retrieval. You are retrieving additional information. So why RAG is important or very powerful is that you don't need to give, let's say you have a corpus of, lots of data. You are not always going to pack all of that corpus of data into the LLM each time a single question is asked. Let's say your company has a lot of data on, it has a lot of policies, all kinds of things, a lot of data, policies, plenty things, right? And somebody is just asking a question on, okay, what's the company's policy on, reimbursement? If I spend my money to do company business, what's the company's policy on reimbursement? Are you going to go and pack data on health policy, on HMO? Are you going to go and pack data on, retirement benefit and pass all of that into the LLM and ask it just because someone is asking a question on reimbursement? No, that doesn't make sense, right? Rather, you will store all of that information in the vector database, indexed by the vector embeddings for each of them. Then when somebody asks a question, you will now use the question itself, create an embedding from the question itself, and then use it to retrieve the closest, most similar matching entries in the database. You extract that. So remember, the embedding is just used as an index into the actual content, which is the actual documents and all of that. You now use that to extract those parts of the document and feed it as a context to the LLM, in addition to the original query. Then the LLM has additional information and is able to answer the question very well. That is why it's called retrieval augmented generation. You are retrieving information and you are using that information to augment the knowledge or the context of the LLM, and the LLM is able to generate the appropriate answer. That is RAG. Every other thing is just procedure of how to implement it. So the RAG and the embeddings will allow LLMs to retrieve and reason over it and give you answers. And yes, we will do a mini project. That one will be today, not today. That will be the task for this week, right? Which is, or next week, I should say, which is, I want you to build something for me. So go and start thinking about it now. That I'll give you documents for you to create embeddings. You make your own RAG. Sorry, you make your own vector database on your laptop. Okay, and then we'll query it, we'll ask a question, and you answer questions based on that document. So that is the end of our class for today. And that is how you implement a RAG. So when we come on Friday, we will actually implement the RAG based on what we have studied today. Thank you very much. I'm going to stop the recording because it's pretty long already. And then we can take questions.